So Source Talks on Kotlin is a community. We're supported by JetBrains, and we're going to be organising regular meetups focused on the Kotlin language. My name's Ben. I just wanted to start by saying a big thanks for turning out today. It turns out that a event on a Thursday evening in December can be tricky, with clashes with Christmas parties, people being ill and stuff like that. So really glad that everyone could make it, although no surprise given the speakers that we've got lined up. So David's going to do first, around about 40 minutes. We'll have time for a Q&A. We'll then just have a short break for a drink and finish off what's left of the food, and then again a talk from Andrey with plenty of time for questions. I'm sure you'll have a lot for him. So first up, David Denton, Google developer expert and co-creator of HTTP. Okay.
Cool. Okay. Hi everyone. Right, yeah. So let's start. Okay, so this is Smash Your Adapter Monolith with the Connect pan. So this is, I suppose, this is to talk about design really more. It's to talk about how we saw a pattern and we saw a problem. We saw some technical debt. We saw like amazing Kotlin language features and how we use those things to actually create a new pattern that we could actually use to make things better. So let's dive in. So first of all, this is me. Hello, it's David. Most of you will know me for HTTP. I'm also Kotlin GDE, as Ben said. I also do Kotlin training, and then like on the bottom is like this is my where I had my expertise, I suppose, from day dot through. I went through C, Java, JavaScript, Python, Scala, and then when I got over doing Scala, because I'm not really a big fan, 2015 started Kotlin. So in 2015, that was kind of before version 1 probably came out. So we were, was it a client? We were actually quite lucky to have an early adopter. So yeah, so it was. I've been doing it for a while and absolutely love it. It's amazing to still be doing it. So what's the plan? So basically, yeah, as I said, we've got this. We identify what we're going to do is we're going to talk about a problem that we came across during actually doing some work for a client project. So basically, this is to do with third-party kind of not just HP, but adapters that talk to other systems. So generally, we'll see when we kind of break down the microservices, we have like front end, middle, and the back end, and the back end talks to other services in the back end, and how we noticed that those adapters that we call them basically they accrue technical debt. And so what we wanted to do is we wanted to take that thing and say, well, how can we take that debt and actually break down what we call the monolith and actually customize the thing, apply different kind of patterns using the Kotlin language features to make things better. So let's go. That's basically what we're going to do. We just basically going to just go through that. But first, some HTTP. This isn't required, but it's probably going to, when we get to the code stuff a bit later, it may be useful for you to know this. So HTTP is a server as a function framework. Server as a function was a paper that was written by a guy called Maris Eriksson at Twitter in 2012, maybe earlier. And they basically, what they did in that paper was to define that every single kind of distributed system or kind of system could be broken down into basic effective functions. And so the reference implementation of this was in Scala. There's a thing called Finnegal, which was used to drive Twitter. Interesting enough, over the last few days, they've actually, Twitter have abandoned their open source thing. So that's going to be interesting to see what happens there. But so we took that pattern, we used it in Scala when I was doing Scala. And then when we started doing Kotlin, we started to try and kind of translate that kind of pattern because it was really neat. It was, everything's a functions, it all composes, it's all really nice. So if you like functional programming, it's really good. But it was asynchronous, and the asynchronicity caused kind of problems. It was confusing to developers. The onboarding was quite hard. People didn't really know how to debug it, and it was kind of stressed. So when we got the opportunity to do it again in Kotlin, we thought we'll start. And one afternoon, Ivan Sanchez, who's like the other creator of HTTP, got together on a hack day and just bashed out this kind of 40-line script that kind of that was the start, and we can show it. It's on GitHub somewhere. It's just this 40-line script. It's heavily TV driven. So I come from like a TDD, the kind of London XP TDD community. So everything we do is all about testing. It's all about how do we test things? How do we make it easier to test? And that's actually a thing that we find is quite rare in various frameworks. People really obsess about, oh, how does it do this? How does it do that? But what they don't think about, and what we find is that you get these shiny frameworks, but they're really difficult to test. And actually, we want to come the other way. We want to say, how do you test this thing first? And it turns out that actually making it easy to test makes the design simple. It makes it kind of like nice and clean. Everything composes nicely, and it all kind of just flows. And what actually unlocks is a load of kind of powerful testing techniques, which aren't going to be in this talk, but we're going to Kotlin Conf in 2013. So we're going to talk about testing HTTP stuff. So if you're going to Kotlin Conf, then we'll see you there. HTTP is lightweight. It's that 1 meg for the core jar, but then we've got another 50 or 60 jars that kind of sit on top of that, which give you kind of various features, and it might be serialization frameworks or templating, or we've got like different servers. So the idea is that you can run things in memory, so that makes your test really fast. And then we've got 10 server backends, we've got 6 server platforms, and it all just kind of composes together. It's really nice. So what does it look like? So HTTP Basics 2, this is effectively the entire core of HTTP. Basically, just those 2 lines of code. And everything else is just like an extension function, or et cetera, et cetera. We use Kotlin features like data classes and like extension functions to kind of create layers and layers on top. But generally and this is like the server as a function mantra, basically. Everything is a function. And you can see here we've got like this is an HTTP handler. So HTTP handler is just a function that takes a request and returns a response. That is the definition of a web server. And then you can apply middleware, or Twitter called them filters, and we decided to take the word filter because middleware is longer. And that's just literally decorating those HTTP handlers. And by layering these things together, we get some really kind of powerful behaviors where you can kind of compose things. So some examples there of creating an HTTP handler, creating a filter, and you can see the composition here where we're basically getting a filter, and then we compose that with another filter, and then we can compose that with a handler to make another handler. So what you're doing is layering these things on top. And then you can call it, because it's just a function, we can call that handler with just a request object. And the request and response objects in HTTP are data classes, which makes them easy to trivial to test, and because you can basically compare exact, because of the semantics of how data classes like compare, it's all completely. So those are the basics. Let's get on to the meat of what we're doing here. Right, so typical HTTP microservice, which we've got here. So we've got kind of 3 layers plus some stuff at the bottom. So generally we have some endpoints, right? So those are the things that receive our HTTP traffic. There might be some business logic in the middle. If you're doing like hexagonal, that would be like called a hub. And at the back, you've got things called API adapters. And then you've got some maybe data access at the top. So at the bottom. So let's talk about the endpoints. So when we say endpoints, this is a kind of a simple HTTP server. Don't worry too much about how it all composes, how it kind of looks, but generally speaking, what we've got here is more composition. We've got like a bearer auth thing and kind of filter, and then we're taking a routing handler, which is a thing that is basically taking HTTP requests and routing them to various endpoints effectively, and the 2 endpoints, Echo and Health there, basically, which are the 2 endpoints. You can see the definition of those 2 things at the bottom, and they're just functions. Yeah, so you've got Echo just returns the request, and Health is like something you might get on Kubernetes. Once we've got that function, we can turn it into a server. And this one we've got Netty, but you can convert that to Undertow or Apache 4, and then you can start it. So until you turn that function into a server, it's just a function. So when you test things, you can test your entire application without actually putting it on network, which means there's no port clashes. You can run all your tests in parallel. It's all totally cool. So that's all nice, right? So we've got it's all nicely factored. We've got like every little endpoint's got its own function, and so we can take them out and we can put them in different files, and they're generally it's nicely constructed, right? So there's not this we do have this kind of composed application, but generally speaking, we could actually test and like exercise all of the endpoints individually, because the actual interface is exactly the same. So if we kind of switch our attention to the back, API adapters. So what we found was that we didn't see the same levels of care, of kind of decomposition, composability in the API adapters. What we saw was that all of the API adapters tended to kind of get like loads and loads of functions. We'll see that in a second. So what we call the adapter monolith. So once again, don't worry too much about the actual implementation. That's the kind of concept that we're getting here. So say you want to talk to the GitHub API. You've got an HTTP core thing, which kind of sets the bearer token, it sets the base URL to be the GitHub URL, and then it takes the HTTP handler. So what this stack at the top is doing is effectively, it basically means that you don't ever have to set that accept header, or you don't have to set the base URL again, because it's done for you when you pass a request. So you might want to do two operations on GitHub. You want to get the user, and you want to get the repo and commit. And the actual details of that aren't particularly important. But the idea is here that we've got one object, which is the class, and it's got two functions. Right? So, and the GitHub API has hundreds of functions. So if we started to, as we use more and more of the GitHub API, the intention, well, not intention, but the kind of general behavior is that this class would grow. This class would grow to basically have 50, 60 functions on it. It will be hundreds of lines long, thousands of lines long. And these functions don't actually interact, generally speaking. They're all individual operations that don't actually, they never really talk to each other. I mean, they might, but generally speaking, they don't. So you can see this is how we would create and expose and actually implement the exercise of function at the bottom. So, real world example, Kubernetes. Who uses Kubernetes? Enough. Have you seen the Kubernetes API? It's quite large. So, the open API spec I put for the intention of this, I put it for the HBA toolbox, and the toolbox takes an open API spec and it generates a server, it generates a client, and it generates some model classes that you would get turned into JSON and sent. That when I did that, well, the first thing I noticed was the bit of JSON was 4 meg, right? And so it was 87,000 lines of JSON, and it had 833 endpoints, right? When I converted that into a Kotlin class using the toolbox, I'm amazed it actually worked, but it ended up with 32,000 lines of code in the Kotlin client, which took 4 gig. Yeah, it took 4 gig. Yeah, I had to up the kind of the compiler memory to 4 gig in order to even get it to compile. IntelliJ just kind of was going, oh, I don't know what's going on here. It's just like red. And that 32,000 lines of code alone, just for the adapter, created a 17 meg jar. Right now, a 17 meg jar is 17 meg is kind of about the size. If you're doing serverless functions, for example, we want our entire application to be 17 meg. Right? We don't want like one jar to be 17 meg. If you saw a 17 meg jar file in a class, you'd be, what the hell is that? But if you had this kind of, when we say the adaptive monolith, that's what we mean. What we mean is that you get this one class and it's got all the stuff in it. And you could break it down, I suppose, into various little bits, but the idea is the same. When somebody uses that client, they have to use everything about it, right? They have, even if they're only interested in one function to get a pod name, they have to generate, or they have to actually import all of the stuff. And so your usage of the Kubernetes API is different to my usage of the Kubernetes API, right? I care about potentially the pod name. You might care about the cluster name or the deployment name, or it doesn't know what it is. Yeah. So that's our real world example. So we saw that and we thought, okay, so what can we do? What we really want to do is take the kind of common behavior of those API adapters and actually break it down in a way that we can kind of split down, so we can decompose it into like tiny little bits where we can easily test it, and we can just use the bits we want, but we still have this kind of core functionality. And the core functionality of an API adapter is effectively, as we saw in the GitHub, it's setting the base URL, it's setting some bearer token, it's setting an accept header, right? That's the kind of core functionality. All the rest of the stuff is just kind of layered on. It's like, get me the user or get me the commit thing or whatever it is. And so, yeah, so these are the kind of what we wanted to achieve. And so we had a think, and we thought, oh, well, Kotlin, we've got lots of like different like nice little things in Kotlin, so maybe we can do something. And we came away and we came up with something, which was the connect pattern. So The connect pattern generally is really simple. It's basically consists of actions and an adapter. And we'll go through actions first. An action is effectively one of the functions that we would have seen on that previous API adapter. So get user, or get repo commit, or in the Kubernetes API, get me the pod details or whatever. So let's look at how the action looks. And the actions the idea of the action is to take the domain request and convert it into HTTP request, send it to Kubernetes or GitHub, get the response back, and then get the stuff you want out of that and convert it back to your. And as I said, your response is not my response, because I want the pod I want the name of the pod, and you want the deployment. But we all have to use, and we will have to parse all of that stuff. So I have to parse the entire response of JSON just in order to get my one field out. And there's quite, if you look at like API adapters, and we do stuff with reflection, etc., but it's quite expensive. You do it again and again and again. Some APIs really return quite like JSON, which could actually just be, you don't even have to process it. Every time you process it, you're processing down into like a bit of JSON, and you're going down into the children, and you're down into the children, down into the children. If it's like multi-levels deep, you end up with this kind of, it's going to take a long time. So, declaring action. In Connect, an action is just an interface here, and it's generified on the R, and R is the response type of the actual action that we want. So, and it's got two functions, and the first function is to request, and the second function is taking the response and returning and extracting out our domain response and returning it. And that's the entire interface, which is action. Let's see an implementation. So we did GitHub, let's do get user. So what we're doing here is we're saying get user, and we want to get username, right? So that translates to get and a users and a username on the end. It's not the exact GitHub API, but it could be close. The things that kind of vary in this are the username. Right? Those are the inputs. And when we come to the outputs, we actually want the user details, and we want the username, we want the user orgs. And these two, username from and user orgs from, are kind of just consider them functions that they're reading the body and they're getting the little bits they actually want. And you see here the data class of the things we actually want out. I want the name and the list of orgs. I don't want the URLs or the latest commit ID or any of that stuff. Or actually, no, and use details. I don't want, the avatar URI or the other thing. What we see here is that also we've got a data class. So data class means things are easily kind of comparable. So we'll see how that kind of comes when we come to test it. But that's effectively the idea, is that you would implement one of these guys for every single operation that you want to actually to expose. And the other bit of the Connect pattern is the adapter. And the adapter is the thing that takes the action and actually takes an HTTP client, and it actually basically is then going to do that operation. It's going to send the request. It's going to send the request to GitHub. It's going to get it out. And it's going to get the domain response out. And that's the operation that we're attempting to actually that we want to achieve. How does the adapter look? Right. So the adapter looks like this. And so this is the interface for the adapter. And the reason it's interface is so we can have different implementations of it, and we'll see how that works in a sec. But effectively, once again, in true like HTTP style, it's just a function. So it's just a function that takes the action wherever it is and returns R, and R is generified on the thing you pass into. Yeah, and we've got a companion object as well here. That's important as well, but we'll see exactly how it works. So with these two things, we've got interface, and we've got interface for action, and interface for the actual adapter, and we've got our implementations of the various methods. So if we want to implement the adapter, we want to re-implement that other API adapter in terms of the new pattern. We can see this. So what we're actually doing here is we're attaching an HTTP version of GitHub to the companion object. And what that means is that we can do this line down here, which says GitHub API HTTP. So that kind of gives us a kind of implementation. If you want another implementation, you can do not HTTP, you can do something else. Maybe you're reading it for a disk or file or whatever it is. Once again, you can see the HTTP kind of setup to set the URI and set the accept header. That is all shared, and that's in here. And those are the same 3 lines we saw in the previous implementation. And our invoke method here is effectively always the same, effectively, regardless of what you do. But because of the generics, we have to basically re-implement it. But it's just this line. This itself is, and because the GitHub API is just a function, we can say, hey, GitHub API, get me a user by creating a get user operation or an action and passing it into our function and getting back the user details. So that's kind of like the same. It's the same thing. The difference is that we have decomposed the transport from the method. Right? So this is the entire thing. It will never get any bigger than this. You can implement 50, 100 operations. It doesn't matter, and they'll just become tiny little functions that are elsewhere. So, however, this API does not look like the other API, right? This is like, oh, we've got GitHub and it's a function. We're going to create this get user action, and that's kind of like, it's a bit weird looking. How does it work? But we can fix that. We can actually recreate the API that we originally had by extension functions because of Kotlin and its amazing, it's got some great features, and one of them is extension functions. I know, it's one of my favorite features. We can effectively just say, well, we can delegate down. So we can say, well, we can add a get user function to any instance of GitHub API, and actually we can just take that username, use it to generate the action, call invoke, and effectively that's exactly the same thing as what we saw before. So if we look at the get user action here, we can see, hey, GitHub get user Octocat. That's exactly the same kind of it's incredibly familiar to anyone else who was using that previous API. It's, and because it's IntelliJ, we have autocomplete. You can do GitHub dot control space. We've got all the kind of functions that we have, but this time the difference is they're all decomposed into all alone small little bits. So compositions, right? So as well as that, what we can do, and we did say before, we can say, we said that those functions themselves didn't really interact, right? So the get user, we had two functions, I suppose. We had get late. We can actually create new functions by composing other functions together. So in this situation, what we're going to do here is we're going to create a new operation, which is our thing called get latest user. And what we're going to do is we're going to say, hey, get me the latest repo commit, which was a function we had over there, and we get the commit, and then we get the author from the commit, and we call get user. And so what it looks like is that we've just added a magical new function onto our GitHub API. But we haven't. All we've done is basically composed two things that already existed together, and nobody that uses our API. So that's the kind of the basis of exactly the entire thing. It's kind of that. So we've got actions, we've got adapters, and we've got like extension functions, and they just kind of compose together, and they just kind of like they work together really well to kind of decompose it. Testing, as I said before, we're really keen on testing HTTP. So we knew that we weren't going to be able to nothing was going to fly if we couldn't test it, or if it was ugly to test or hard to test. And luckily, this is trivial to test. So let's see how we do it. So we want to test an action. An action, remember, has only got two functions. I'm going to take some inputs, I'm going to create a request, and I'm going to take a response, which is effectively, in our case, it's like a string, a bit of JSON, doesn't really matter. And we're going to basically, so the two functions are get the user, what kind of request does it create, get the response, what's the user details that come out the other end. Basically, and because we're just using data classes, the data classes, they will naturally be really simple to actually to test because they've got that equality thing. So we can just use regular Hamcrest or strict or whatever you want to. So that's testing in action. Mocking. So everyone likes, some people like mocking, some people hate it, but because our GitHub API is an interface, it means we can mock it without any kind of horrible power mock stuff going on. We can use a standard mock here. This is using mock K. We can set up an expectation that when we call the GitHub API with a get user, it returns the user details. The user details we know is a data class as well. And we can just do an assertion to say, when I get the user Bob, I equals the user details. I'm aware that there's nothing being tested in this class, in this test, but it's going to be showing effectively that this is trivial to do because it's just interface kind of mocking in exactly the same way that we do it all the time. Stubbing. So another option is to stub the thing, and so stubs fakes. People get confused with them too, and it's probably like not that much of a kind of that real difference. I'm sure kind of came back and Uncle Bob would kind of say there was, but anyway. Generally speaking, we can create a stub or a fake GitHub API, which has got a little bit of like in-memory state, and we can use a bit of when, and because what we can do here is actually say, well, we can delegate down once again into when we've got an action and when it's get user, then we can say get the user, and we can interact with our little in-memory state machine, and we can return the right thing. And here we're just looking up some stuff in a map. Yeah. We could, if we made the GitHub API sealed interface, then we could get rid of this else because we would have exhaustivity. But if we did that, the problem with that is that you would end up having you wouldn't be able to then effectively extend it to create your own functions because the sealed interface of the action would be the thing that knew that all of the implementations up front. So there's kind of like a little bit of a wrinkle, but it's there. And this allows you to just implement the ones you want. Right? I don't have the GitHub API with 50 different methods on it, and I only actually want to implement 2. I'm not interested in the other 50. So normally what might happen is you'd get 48 things with to do, and you'd play hunt the functionality. But with this, you can actually, this is like 5 lines of code. Perfect. Decorating. Once again, also because it's just interface, you can decorate stuff in exactly the same way that you would decorate. You could decorate any other thing. It's an interface, so you can just take a delegate. You can use by in order to do it, I suppose. Same thing here. What we're doing here is basically just we are recording all the actions effectively as it comes through. We're recording the actions to a list, and then we're kind of just delegating down to the actual action. So we're doing recording, and you can record the request, you can record the response, you can do what you want with it. You could actually, we've got a list of then interactions that happen, but the sky's the limit with exactly what you want to do. But once again, just in space, so it's trivial to do. And once again, there aren't 50 methods on this thing. There's like 1 method, so it's really easy to just do the bits you actually want to do. Varying program models. So the problem with I suppose with this implementation previously was that what happens when something goes wrong, right? So R itself is a type, but maybe we want to use result classes. Maybe we want to use a result monad, and it could be result for K, it could be the Kotlin result, it could be an arrow result, or either, whatever. Doesn't really matter. But what we can do is actually then, this is result for K version, we can actually vary if you want to use results, then we can, using result for K, we can do exactly the same thing. The only difference between this and the other version was this result on the result type, where we've got result of R of exception. And you can, make it an either or whatever you want. Doesn't really matter. And once again, this looks exactly the same as the previous implementation. The only difference is we're basically we're saying from response, if it was successful, then we're gonna say use details. So this is basically checking the status of the actual response that came back. So if it's a 400 or 500, it will do something else. So if it isn't successful, we're going to basically return a failure. So we've got our kind of monadic kind of result stuff if we want to use that model, but it doesn't matter because we've got the choice. So summary: we've got simple modular adapters. They're testable and composable. They're flexible and model, and they'll actually work with any request response protocol. So it doesn't have to be HTTP. It could be anything. It could be a database connection or FTP or anything else you can think of. The pattern itself remains the same regardless, as long as it fits the request response model. You're all good. So the reference implementation. So we did this, and we decided to say, well, where can we use it? And actually, one of the things we wanted to do was to use. This was when we started using HTTP in a serverless environment, and we wanted to get we had some lambdas, and they were talking to S3, and they're talking to STS, and they're talking to Dynamo, and whatever. And the Amazon SDKs are really heavyweight, right? We're talking a few meg, and you've got Jackson, which is like, and then when you get Kotlin reflection, that meg, I think that's 2.5, 3 meg on itself. So the nice thing about what we decided to do is, well, we can actually create some adapters ourselves. We can apply them to all the services we need or we use, and we created a bunch of adapters. So HTTP Connect is effectively a kind of an alternative SDK for using any service you like. But I mean, we've implemented a bunch of AWS services. They're featherweight. So instead of a jar file which has got 3 meg of stuff in it, I think the SSM jar is, yeah, it's many megs. I'm not sure, but the SSM HTTP Connect is a couple 100K, right? And it's no reflection. So and we're only using the bits. You can use just the bits you want, right? So if you only want that one field from that big XML thing, you can implement your own little adapter, and it will just use that. It will just pull out that one field instead of having to parse loads and loads of XML or JSON or whatever. So the zero reflection stuff was really helpful, because what it allows you to do is we can do serverless, because we've got, as I said, we've got like our entire functions that are just or that become 11, 12 meg instead of 30 meg, 40 meg. And also with Graal, because we can use zero reflection. I don't know if anyone's used Graal VM, but basically reflection is what they would describe as a bitch when it comes to Graal. If you have to do any reflection at all, then you have to register reflection every single class in like a little reflection config file. And what we actually see is stuff like Micronaut and the various other people that are doing these kind of conversions. There's a runtime step to create and generate this thing, and it's pretty gnarly, and it's not particularly pleasant. Every time you add something, you might need to add another bit of reflection config. It's a nightmare. However, if you don't use any reflection and you just have completely lightweight stuff that doesn't do anything clever because it's all statically generated, we use compile time Moshi adapters. So we use Moshi over Jackson. Moshi is once again like 300K. You can use it with reflection, but you can get it to actually generate the adapters. So once again, you're going to end up with a function it can be talking to 7 or 8 different services, but the jar file that you generate and then upload to Amazon, it's like 12 meg. And so because it's only so small, the actual spin up time for Lambda is also really expensive. So Jackson itself adds 1 second, I suppose. And the interesting thing with AWS is that there's an implicit internal Jackson in the runtime also. So you're always paying that cost. So if you can avoid that, which is why we wrote another runtime for HTTP, but then all the better. And I think last week they came up with SnapStart, which is yet another thing that will allow us to kind of really start using JVM stuff in a serverless environment. Now, up until now, all the Go and Node programmers have been laughing and going, you can't do that. You're ridiculous slow startup time. But actually, AWS has obviously worked out that Java and JVM programs are probably a big market, so they've decided to actually put some effort in and make it decent. The other thing that Connect does is it's kind of connected to the HTTP kind of ethos and testing, which is to write fakes. So we write in-memory fakes. So we've got an in-memory S3, we've got an in-memory KWS or KMS, we've got an in-memory SSM. What that means is you don't need local stack. Right? There's no local stack required, no Docker. You can run everything in memory, in parallel. It's all fine. And the implementation of the S3 in memory, it's a map. So it's literally some bytes against a string, and the string is the name of the file. So that stuff is, this is not the reference implementation. So go and have a look. It's all good. And that's it. So pretty much, hopefully that was sensible. Are there any questions? Hello.
Okay, I get to start on here. So I actually have 2 questions.
Yep.
One is HTTP free and quick. I know that you're leveraging. But is it influencing the design of HTTP 4K, or is there something that we should worry about?
Not yet, no.
Not
So not yet, but we haven't really started to think about it because the vast majority of what we see internally are everyone is still using JSON, whatever. It's exactly right. So it's like once we get there, then it will be. They seem to keep like changing their minds about stuff, right? So as well, it's like HTTP2 push. That's dead now. Okay. Anyway.
The second question is, you mentioned Growl, but then you mentioned jar files and things like that.
Yep.
So how are support for native images? Can I just deploy native image to a Lambda?
Well, so we built a runtime, and so you can. I think Growl, as of a couple of weeks ago, now supports Java 19. I think so. I think 22.3. We've pre-built a Docker file basically that does all the native stuff inside. So basically, what you do is you supply it. You supply a zip file, or I'm not quite sure the thing, but you actually it's literally one command. I think it's a shadow jar actually. Yeah, I think it creates a shadow jar, and then from the shadow jar it creates the Growl native thing, and it pops out a binary at the other end. And the thing is, it takes a while, right? So that's the other thing. The Growl compilation, a couple of minutes, and that is even worse if you're we're talking about it takes a couple of minutes for something that's 13 meg. You do it for something that's 100 meg. I don't know how long it takes. I know it's pretty everywhere. Okay. Anyone?
So for a sizable API, I can see that we can implement just the bits that we want.
Yeah.
But what's the how do the sizes compare if I implement all of an API with all these little adapter bits compared to just methods?
It's probably, yeah. I mean, it may well be bigger. Now the question is, how are you gonna, how are you gonna test it? Do you actually want to actually implement it? The nice thing about this is that actually, as I said, right, your version of what you want from any endpoint is different to my version of what I want. But this gives you the opportunity to actually do exactly what you want. The thing that's common is the setting up of the HTTP client. It's the adding the URL, it's adding the bearer token, all that stuff, right? Well, that stuff is the stuff that's common. And actually, if you look at the classes, that's all it's doing. The class, as I said, the functions don't interact. So normally, that I've seen. So it's just, I think it's to do with when you've got 15 methods on a thing, it just starts to, the tech debt just starts to grow. And it becomes unloved, I suppose.
But where you have shipped an entire API, I guess, then we can strip out all the bits we don't need, even though you've generated all that stuff.
Yeah. Yeah, I mean, there's nothing to stop it. So what is nice is that you can say, okay, here's my API, and my API requires this arcane authorization protocol, right? It sets something and it does some kind of bearer token nonsense, blah, blah, blah. You only have to ship the interface and the action and the adapter. You can ship nothing if you want. You can break up all the things into various bits. You can. I can go in. I can implement my version. You can go in. You implement your version. You don't get that flexibility if you have just one giga thing. And the 1 giga thing forces you to, because I don't know when I wrote it. I don't know what you want from get user. I know what I wanted, but I don't know what you wanted. So maybe I just didn't do that. So it's kind of, you get the option to implement exactly how you want. And it doesn't matter. You can use JSON or Jackson, or you can use Mosh. It doesn't matter because it's just that tiny bit of code that you can implement, and it's not scary. It's kind of, they're small and they're modular. And because of the beauty of Kotlin, we can do this stuff, right? Where it just looks, and nobody's scared, and it also looks, a bit like, it just looks like you just create a new thing and you call some functions on it. You don't know the difference at all. What we actually do in Connect is to regenerate the stuff. So we have a thing. We have a little kind of compile time thing that actually generates using cats. It generates the kind of fluff basically. So we don't have to write either. Because nobody likes writing that stuff. I mean, this is they can't manually take out all the things and put them into a class and call and invoke on it. It's just no one wants to do that. Anyone else?
This might be a silly question. when you implemented the action interface, you used the data class.
Yeah.
At that point, you said it's better for comparison, but I didn't quite get that. Why choose this data?
Well, remember that when we mocked it, yeah. So when we mocked it, this guy, we said any get user there, right? But actually, you could say any get user that's exactly this thing, or it's this thing with the username set to that. It just gives you options of doing it. But I mean, it's kind of, I say it's free, but it's not really free. But I mean, you get the option to do what you like. We decided to do it because we thought, actually that's a thing, and we can it will potentially give us options of, it gives us that stuff, that functionality for free. It doesn't, doesn't take anything away. That's why we decided to do it.
Thank you.
That's okay. Anyone else? Or are we done?
Thanks for the warm welcome. Just a short apology. I may start coughing as I talk. I'm long recovered from the cold, but the cough has not gone away. So I'm not contagious. I checked with my doctor. You're safe. Yeah. That being said, today we'll be talking about languages we learned from when we worked on Kotlin. And I'll give it just a very short introduction, and we'll start with examples, the entire rest of the talk. Feel free to ask questions as we go, so just put up your hand, and I will be inviting questions, making special breaks for them, so just feel free to make it a conversation. All right, short background on myself. I started at JetBrains when Kotlin was starting, so basically I was hired to start Kotlin back in 2010 and worked there for 10 years. Led the team, led the design of the language, wrote huge chunks of the slow compiler everybody hates. And better people are fixing this right now. Currently, I'm not with JetBrains. Nothing I say here is official. But still, I can share what was then and my personal opinions on other stuff. So I'm not speaking on behalf of anybody at JetBrains at the moment. The main motivation for me to give this talk is this. Like, this is what internet is like in general, and in particular when people talk about programming languages they prefer. And the conversation, if you can call that a conversation, usually progresses like this. I love this language, and you seem to like that other language, but that other language is no good because it stole all the ideas from my language. And from a language designer's standpoint, this is ridiculous because, like, this is what we do as engineers in general. We look at other engineers' work, we'll learn from them, and we try to fix it. And so basically, the initial motivation for this was to just openly say, yes, we were like normal engineers learning from others, and we're proud of it, and I encourage everybody else to do the same. Just a small note that I don't think that originality itself is any good for anybody. Like, unless you're an artist, which I'm not, you're not after originality at all. Like, the most original language in the world is brainfuck. Yeah, so just let's build in each other's ideas. If you like any idea from my talk, please use it in your work. This is what ideas are good for. And yeah, I'm happy to give credit to people I learned from. One important thing to set the stage for all the rest of the talk is the premise that existed back in 2010 when we started working on Kotlin. It was basically this motto that we used for Kotlin for a long time. We wanted to make a pragmatic language for industry, and every word in this formula matters. So it's there was an emphasis on being pragmatic, as opposed to being driven by novel research or being mathematically beautiful or anything else. Mathematical beauty is perfect, and we are not. So to us, the usability, the practicality of the language was much, much more important than any elegance. And the industry setting was also very important. So we wanted something that many people would use and would like using. So we started from the JVM premise. Back in 2010, Java wasn't in great shape. It was a very difficult transition from Sun Microsystems to Oracle, and the language wasn't progressing much. Everybody was pissed as hell because of years and years and years of dated language not being updated. And that created the window of opportunity for Kotlin. And fortunately, we built enough difference into Kotlin that it's still relevant today when Java is already at a very good pace in terms of progress. And like, big kudos to the Java team, because the guys are doing great things there. Still, we can coexist, and different people will benefit from different languages, and I like that. Still, those people on the internet, those with pillows, sometimes play this nice game that I want to play with you too. It's called Kotlin is just. And here's the first example. What do you think? What language is this?
Ruby.
Ruby. I don't think Ruby would allow this. C. C, not quite, I think, because of this dot here. Java. Java would work. C++ would work. Any other languages? JavaScript would work, or Kotlin would work as well. So one could say, well, this is Java. One could say that Kotlin is just Java without maybe all the ceremony or something. But the game doesn't end here. What language is this?
Scala.
Yeah, this is Scala or Kotlin. Yeah, so this same set of characters compiles in Scala or Kotlin. So one could say that Kotlin is just Scala without all the nice things. Or just Scala without implicits and hard kinds and pair matching and view bounds and monads. Or Scala without all the stuff. XML literals, yeah. That's a good one. Another example, what language is this? Kotlin, yes, learned that. What other language is this? Swift? I'm not sure. Groovy, yeah. So, say it again?
Except the method.
Okay, yeah, except the method names, but still, this is compilable in Groovy. So one could say that Kotlin is just Groovy without all the mess. I don't know. What language is this? Kotlin, but what other language is this? C#, correct. So one could say that Kotlin is C# without all the Microsoft. I don't know. Yeah, so we've seen a few languages. So this doesn't work with Python. Python is too original in syntax. But still, all these languages had a lot of influence in Kotlin. And today I'll be showing different examples of how ideas from different languages combine in Kotlin, because it's one thing to learn from someone, and then another thing to combine things you learn from different people and put them to work together in the same language. And just for context, here is a timeline of how things progressed. So this is the timeline from 2010 and through 2016 when Kotlin released 1.0. So Java throughout this period was initially 6, then 7. 7 is a very little update in terms of the language. And then we weren't quick enough to release Kotlin before Java 8. It was a problem marketing-wise, but still we survived, and it's good. So we saw Java 6, 7, and Java 8. We actually participated in the design for Java 7 and Java 8. Oracle runs an open process there, and I was a delegate from JetBrains to this working group, so it's all there in the mailing list. So this is Java. Scala was 2.8 through 2.11, and 3 was in the works, but a very early stage at that point, I think. Groovy went from 1.7 to 2.4, which means they introduced types and many interesting things during this time. Swift existed, was being worked on, but was secret for a long time. And so it was only in the very late stage of Kotlin development when Swift was published, and we saw so many interesting things and so many similarities. And I would have loved to look at Swift before that time, but I couldn't. And there are actually a few things that we should have done differently, and the Swift team got much better. But it's too hard to change at this point. C# went from 4 to 6, so many interesting things were getting into C#. And I'm happy to see that some things are getting back from Kotlin to C# now. And well, Python is complicated now. But the point of this is that 3 already existed and was known, and all the features there we could look at. Okay, any questions at this point? Go ahead.
Where did the name come from?
Say the name. Oh, the name for Kotlin. Yeah. Okay. So today, this morning, I learned that the letter K is somehow special in the English language because very few nouns begin with it. So it's somehow very beneficial for brands to start their name with K, and many brands deliberately change the C to a K to stand out and be remembered. And some people claim that this is how the word OK stuck. Yeah, but we knew nothing of that at the time. So Kotlin is a name of an island near St. Petersburg, where I'm from. So the core team of Kotlin worked from St. Petersburg, Russia. And the logic there was kind of convoluted. It was a nightmare to pick a name for a language, because it's generally a nightmare to pick any name. And the initial code name we used was Jet, because of JetBrains. But then it turned out that the trademark was taken by someone else, and we had to come up with something else. It was agony, like at least half a year long. I don't remember how long. And then, so we basically had a deadline because we had to publish the description of the language with the name. And I was writing a wiki style thing in Confluence for Kotlin, and I created a separate page for the language name because I could rename it later, and it will rename across the whole thing because it wasn't fixed. So the island thing came about through the idea of another language. Gavin King was working on a language he called Ceylon. And his idea was that Java is an island with coffee and Ceylon is an island with tea. And Dmitry Zhemerov, my teammate, said, okay, we don't have tea or coffee here, it's too cold, but we still have an island and it's very beautiful. So let's use that. And it's not Googleable in anything. It's like there is a single Wikipedia page and nothing else about this. Turns out any word you pick is a bad word in some language, or at least a part of it. So I'm told that there are some bad connotations for Kotlin in Chinese, and Kod is a bad word in German and whatnot. But we were like, okay, we can't do this anymore. We'll take this as a code name, and we'll change it later if it's too bad. And of course, nobody got around to changing it ever because, not again. So yeah, go ahead. Yeah, I'm not sure there is a precise answer to this question. So the question is whether we considered Kotlin multi-platform at some of these stages. I think the idea of multi-platform was there fairly early. Probably around here, we already were talking about multi-platform. And at some point, we started Kotlin.js as an alternative backend just to make sure that we're not tied to Java too much in the language design. It helped maybe 70% of the way. It was still very Java-centric, and we had to fix many things later. But the idea was there. Like the multi-platform as it is today is the philosophy of common versus platform-specific declarations and different implementations for different platforms. That came to be, I think, much later than 60. But the idea of different platforms and compiling the same language to JavaScript or native or something else was there from very early days. And I think there are still people coming to the Kotlin team asking about compiling Kotlin for CLR, for the C# and Visual Basics runtime. But that's so much of a pain. I mean, it's not because CLR is bad. It's very good. The problem is to make CLR is made to be so different from Java intentionally because of all the IP stuff. It's going to be so ugly in Kotlin. And you'll have to jump through so many hoops to make it work. So that is probably not an option. But yeah, JavaScript and native were conceived, I think, somewhere around 2013, and JavaScript was implemented before 16. Native was started a little later.
You mentioned C.
Yeah.
Funny enough, some of probably the only feature were you guys looking with the time or?
Yeah, so the question is, were we looking at Ceylon at the time? Yes, we were. And actually, there was, Kevin wasn't happy with us looking at it at the time. Yeah, but interestingly enough, we couldn't learn much because it's interesting. We actually consulted with the same university professor about types and took similar ideas very differently, because so basically the philosophy behind Ceylon was, let's try and make everything nice and shiny from the ground up, use only the runtime, don't use any libraries. And they were trying to make this like very nicely designed ecosystem from scratch. And our approach was 180 degrees from that. We're trying to reuse as much as we can, make all the libraries work, make Kotlin mix with Java very easily, and all that. So all the design choices on the language were very, very different. And, there was one thing we tried to implement at some point in Kotlin. Ceylon had this very nice idea of basically of annotations without @ signs in front. So basically, their annotations looked like modifiers. And the early implementations of Kotlin had this, like, let's not distinguish between annotations and modifiers. That's a nightmare from the ID perspective. We dropped it, and yeah, it's a nice concept, but we couldn't figure out a way to efficiently support it in the tool. Mm-hmm. Okay, so this is a very specific question. So if I understand you correctly, it's about variadic generics. Like, can we have a generic type of not one T, but a vector of T's? It's actually on the table for Kotlin, but it's not very simple to implement, and it's not so beneficial that it would be very high up the priority list. Okay, more questions are welcome later. I'll just go on with the talk. So, okay, from the very introduction, what do you think? What language influenced Kotlin the most? Okay, I'm with the folks who say Java, because it did influence Kotlin very, very much. Scala had a lot of influence. C# had a lot of influence. Others too, but Java much more than anybody else. So my examples will show some key ideas and where they came from, and I'll try to illustrate the issue of fitting them together. It's not always easy, but I'll do my best. Let's start with like the surface with syntax. And so to begin with, the language design in general is maybe even more about what you do not include in the language and what you leave out from existing languages. So here are some examples of what we left out from Java. C-style fors are hell. Just no C-style fors, please. We should have probably kept ternary operator. Yes, but we didn't, and we kind of cornered ourselves and can't put it back in. Sorry about that. This is evil, of course. And bit shift operators, we just considered them too exotic for mainstream, and we could use the token for something else. I think bitwise ors and ands may make their way into Kotlin someday. They're actually on the roadmap, very, very low on the priority list for years. When we looked at Scala, there were very many nice things we took, and I'll show you them later, but a few things we didn't. And so this thing the invisible lambdas, implicit lambdas, is very elegant in many ways, but it enables very cryptic code. And I have a history of debugging a single line of Scala for 40 minutes because I couldn't figure out those and implicits together. It scarred me so much that I decided that in Kotlin, like every lambda will have clear curly braces around it, so that there is never any question about whether this is a lambda or not. Also, ASCII art, of course, is great and everybody loves it, but it's probably not for mainstream programming. I'll talk a little more later about the array indexes and how this syntactic thing is actually tricky and interesting, but Kotlin does have this. We have normal square brackets for this. Any questions about things left out?
Actually, Michele mentioned tuples. We had like Kotlin. I remember that it had support for.
Yeah. So the question the question is about leaving out tuples. At some point, there was a special syntax for tuples in Kotlin. I think it was some of the milestones long before the first release, and they they were slowly drifting towards being almost like data classes, and we just dropped them because we couldn't explain to people why they should use one or another. So it was simply redundancy. Another question. Okay, implicit parameters. Why do we leave out implicit parameters? Where do I start? So basically, I think the overall concept of implicits was the biggest issue with Scala that people at JetBrains had and many other people in the mainstream had. Because basically, Scala is very clever about figuring out implicits here and there, but people are not as clever. And sometimes it's very hard to understand why it's not happy. It's very hard to understand why it's happy, but it's not doing what you want. And especially in somebody else's code, it's very hard to figure out what they meant implicitly here. So this is basically a nightmare for the tooling, for people, for maintenance, for everything. And we deliberately wanted all the things that are sometimes explicit be always explicit in Kotlin. It was also a deliberate choice, a lesson we learned from Scala. Okay, so another lesson we learned from Scala was types on the right. And it was actually one of the most heated discussions in the early Kotlin community. Like, as usual, people don't care as much about the deep things. They cared passionately about superficial things. And there were people who like really passionately advocated for like a language with types on the right will never fly and things like that. But we knew that people like Scala. Scala is fine. I learned Pascal as a school kid. It was fine. So we were reasonably sure that types on the right will get familiar and people will be happy. Technically, it's very important for a language with type inference to have types on the right because you can omit a type on the right very easily, unlike introducing the word var or auto or something on the left in C-style languages. What was a lot harder for us was the fun keyword. Nobody on the team is a native speaker of English. And we were like, okay, so fun is a word. And we kind of don't like the other options because function is very JavaScripty and fn is too short and makes guns and you know. And func is 4 letters and other val and var are 3, so we want things to align vertically and so on and so forth. Fun fits nicely. But now, is it okay for English speakers? Like, especially since we have, we can say like private fun in Kotlin. or public fun. Or explicit fun. Or public actual fun. Or, you know, all these things. And we're like kind of on the fence. But one language helped us out. Do you know what language it was? A programming language that has fun for a keyword. It's very academic. It's called ML. And it's one of the most prominent functional languages of the like early functional era. And fortunately, the person who created it, Robin Milner, is an Englishman, and we believed in his judgment of the language. So it was settled, and now all the jokes about fun are legitimate. So they are there on purpose. I'm not exactly sure what protected fun means, but I think it has a meaning. Another example of like a syntactic decision that was kind of difficult for us because technically it was very easy, but we didn't know how people will take it, is this one. What do you think? Which language influenced this example? Python, right. Python, because to create an instance in Kotlin, you don't have the new keyword, unlike Java and Scala and C++ and C# and so on and so forth. And we just looked at the grammar at some point, and syntactically, we didn't need the keyword. There are reasons why C++ and Java have the keyword there. And in Kotlin, the grammar allows you not to have it. We were like, OK, so Python is fine with it, without it. And one less keyword, it's nice. But then it was a huge cultural debate about like whether you actually want every object allocation in the code be marked with something special, so on and so forth. And it like went back and forth for quite some time. And we actually did analyze some of the Python code bases to figure out whether it's so bad or not, and settled on not bad. And got a lot of perks out of that because we can now overload constructors with functions and make nicer DSLs and so on and so forth. As a byproduct of that, speaking of making different ideas work together, as a byproduct of that, we needed what's called anonymous inner classes in Java. And in Java, the syntax is based on the new keyword. So you say just new class name, arguments, and then curly brace. And the parser knows that this is creating an anonymous inner class. In Kotlin, there is no new keyword. So we had to come up with something else to allow these literals somehow. Fortunately, we had an object keyword from Scala for a different reason. So we decided, OK, this is actually creating an object because the class doesn't have a name. So it's basically just an in-place object. You specify the signature, and there you go. It's a little longer than the Java version, but I think the news in front of constructors pay off this debt. Any questions about this? All right. So this is from Python. Let's move on to some more interesting things. As you know, Kotlin has top level or free functions and properties. This comes from many, many languages. Basically, Java is almost the only language that doesn't have them. But to interop with Java, we have to introduce some spells to make sure that those things are exposed nicely to the Java world. So this is basically, again, making things work together, but more on the API level than on the syntax level. Then, an interesting question. So what's a function that returns nothing at all? And I know that in the 1970s, Dennis Ritchie would answer like this is a function that returns nothing at all. The problem is, for all the greatness the C programming language brought into this world, I think in this particular case, Ritchie was wrong. And we have a very weird situation because of that. I'll try to illustrate it. So first, I'll try to explain why this function actually returns something. So here is another function that's a higher order function. So its argument is a function, and it just calls that argument and returns what it returns. What do you think this statement will print? So I'm taking the function, passing the main in, and what will be the result? You're saying unit. Any other? Nothing. Interesting. So you mean the word nothing? OK. Any other attempts? Void. Interesting. It's actually Kotlin.unit. So you're mostly correct. And so this means that this function that we passed here as a value actually returned something. It was an object of this class. Actually, it's two strings. So the object called unit is defined like this. And by the type signature, the main function returns unit in Kotlin. So basically, we use unit as nothing interesting. So it's not, this function doesn't return absolutely nothing. It returns, but it doesn't return anything interesting. That's why we don't specify it here. We just say return, because this is all that matters. It returns. Doesn't matter what it returns. We could say return unit explicitly. And there is a function that actually returns nothing. It doesn't return at all. Like, there is no path that returns any value. And this is why the type nothing exists in Kotlin. If you have an infinite loop, you return nothing. If you throw an exception, do nothing else, you return nothing. And actually, what can we write here instead of 3 question marks? Is there an expression that would constitute a value of type nothing? Throw, you can say throw there, yeah. You can say break there, actually, if you have a loop around it. You can, of course, call any other function that returns nothing. And you cannot say return, but you can say return, 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 throw exception. So basically, the idea is that if whatever you say here breaks the control path and the return doesn't execute, there is no return, the type is nothing. So why I'm bringing this up here is because many people are still confused with the word unit and the word nothing. And why in hell wouldn't you use the normal word void? And here is a table that illustrates the problem. So as far as I know, the word void means nothing or emptiness, and is kind of signifying an empty set. So if we take the set semantics for types in our programming language, the meaning of the word void would correspond to an empty type with no instances. And the type void, as it is in C or Java, is not that. So it actually kind of means that the word void is banned from any further developing programming languages, because it's wrong, and you have to either stick to wrong or change the meaning of a very, very well-known word, which you don't want to do. So basically, when we say void in Java or C# or C++, we mean nothing of interest, but the word says nothing. So there is a solution. You can say nothing for nothing, and it means what it says. And this is how it is in Scala and Kotlin. But you're left with this nothing interesting type. And I would love to call it nothing interesting, but everybody would hate me for such a long word. So basically, we didn't have any good solution for it. And Scala proposed a mathematical thing, unit, which is like one of something. Technically, it's a tuple of 0 elements, of all things. It's like an algebraic term. It means just a singleton of no significance. We kept it just because we didn't find anything else. I would call for proposals in this room, but it's late. Yeah, so this is how simple things get stupidly not nice, just because of history. Any questions? All right. Who in this room uses extension functions in Kotlin? Any hands? Nice. What are you using them for? What's the best use for extensions? Okay, so basically defining functions that belong to the same API in different places. Okay. Rewrite an API. Okay. if the API collaborates, you can, yeah. Any other use cases?
Yeah, nicer to call.
Nicer to call than what?
DSL, maybe they allow to create also DSL.
Yeah, you can add DSLs on top of existing things. Yeah. So other things that people say is monkey patch libraries in terms of dynamic languages. That would mean adding runtime methods to libraries, which you can't do in Kotlin actually, or break encapsulation. You can't do that either, but it looks like you can and makes it powerful. And it does get rid of util classes in many cases. So for example, the string class in Kotlin is very, very small because all the methods that are there for Java or Scala are extensions. And it does give you a nicer code completion, but these are kind of on the side, nice to have things. And the main thing was, like the main reason why we added extensions to Kotlin was different. We wanted to keep APIs minimal. So basically the philosophical idea of having such a thing as extensions in a object-oriented language is to keep your interfaces small. Because if you don't have extensions, you basically, for convenience of your users, you have to add those helper methods into interfaces, and it gets ugly. Interfaces get huge, and it's hard to see what is the actual abstraction there and what are the helper methods. And this is the main reason. So we didn't invent those, and C# and Scala had some way of doing the same thing, minimizing interfaces through providing methods callable through a dot from the outside. But there were kind of issues with implementations with the approach taken by C# and Scala. So for Scala, at that time, it was very scary because it basically meant that to add an extension function, you need to create a new class, and this class gets instantiated at every call site. So basically, every call of an extension function is an object creation, which is scary. They learned to optimize it over the years, so on and so forth, but the concept was scary. Didn't want that. In C#, it's basically the way Kotlin compiles extension functions, but the syntax is pretty C#-y, Java-y, with a lot of words. And this idea to qualify the actual parameter with this is actually nice, and we took it and used it in Kotlin. But the general syntax, we tried to make it more intuitive and more more similar to the call site. So this is how we ended up with extension functions like this. It's probably one of the most successful features in Kotlin, and I'm very happy with how it turned out. Any questions about extensions? Okay, so thanks to Scala and C#, great ideas. Yeah. Oh, hard to pick the biggest. Well, actually, I think that there are issues when people when people make specialized libraries with very generic names of functions. Like if you do something with hardware and call it filter, it's a bad idea in general, but people do it. And I think this can mess up your compilation errors quite a bit, because you'll be like, okay, here is 50 candidates that didn't fit, and just one of them right there is my hardware thing, and all the rest is standard library with all the collection functions. So I think this would be the biggest, yeah.
So it is coming up, but the multiple receivers for the. What do you think about that?
I think that we very much need to generalize the idea of receiver. I think the design that's been published recently is an intermediate one will change, because having 3 different notions for receivers is a little too much. I think we can unify them. I did speak with the folks on the team, and there are different ideas around it. So I think it will get into the language, and it will be a little smoother than it is now.
You kind of say, okay, playsets were complicated and things like that, but isn't context receivers kind of trying to do the same thing under control?
Good point. Yeah, so the question is, if you're writing context receivers in Kotlin, how is it better than implicits in Scala? Well, it is, how to put it? So one thing is it's strictly weaker than Scala. So Scala is scary with those implicit objects that can inject everywhere, anywhere, and it's crazy. So nothing like that is happening in Kotlin. It's one thing. Another thing, so Kotlin's implicits are scoped. It doesn't mean that there is no implicitness going on. There is some implicitness going on, and this is a trade-off. Like we started with like, let's make everything explicit, and then the extensions were so nice that we added them, and now we're generalizing that. And you're right, we are drifting towards more implicitness, but I think we still keep a reasonable amount of it.
But I really like to say, because sometimes it's probably where, go back to that, and I want to, I want to allow one function at a certain point, and not be callable from So is this something like, I mean, I'm probably doing something wrong. We or I can say, hey, this body function is with the context of HTML, whether we move to but it's not available if a or image is actually like an exclusion.
Okay, I'll give a little background on this, and I will not answer your question in full, but I'll get back to it. So we started, after extensions, we started talking about DSLs, and the most interesting DSL in Kotlin, DSL type in Kotlin is type-safe builders. And this is a carryover from Groovy, and was actually an explicit goal very early on. Folks over at JetBrains tried Groovy in many settings, and builders were great, but they were dynamic, they were not type checked, they were expensive at runtime. So there was an explicit design goal. Let's try to support Groovy-like builders, but static and fast. Not bad, right? And interestingly enough, we figured it out. So basically, this is the thinking that happened in Groovy. So we didn't invent any of this. The ideas, syntactical ideas from Groovy were very nice. In Groovy, if you have a lambda at the end of your argument list, you can specify it outside of the parentheses, and you can omit an empty parentheses. So basically, you get this nicer syntax, more like fluent syntax of calling higher order functions. And this if keyword also sort of shortens your notation. It's nice unless it gets crazily nested, which we didn't figure out anyhow. So you can get things like this. You can get like language construct-like things like lock of foo. That's very nice syntax. Question is how you make it work. Because you need to somehow explain to the whatever lambda what its context is and what you can and cannot call in this context for a builder. So a builder looks like this. This can work in Groovy, it works in Kotlin. And you cannot call body outside of HTML. And you can't pass anything but the actual supported attributes to an A or an image. And how is this working at all in Kotlin? Many of you know the answer, but I'll pretend that I'm being very dramatic here. So the basic idea actually comes back from Pascal. When I was a school kid and used Object Pascal, there was this language built-in construct called with, when you could basically not say foo.bar, foo.baz, foo.cooks, and you could say with foo, bar, baz, cooks, and it was great. So in Kotlin, this is a library function because we just took two very well-known things, an extension function and a lambda, and put them together, making extension lambdas and extension function types. So with in Kotlin is a higher order function with body, which is an extension function, extension lambda for t. So since my curlies here are an extension function, they have a this of type foo. It has bar, bars, and cooks. I can call them, and I can omit this. So great, Pascal is here without any compiler work. Isn't it nice? So good question is like, how do you control what can and cannot be called down the line? So can I call a method from HTML inside of an anchor, for example, or inside of an image? So the answer is, a lot of the time, you can play interesting tricks with some annotations and some types and so on and so forth to make it mostly discoverable for the compiler that a call is illegal in this context. It's a witchcraft, honestly, but some people mastered it and put out their libraries. Ktor is very good with this, so you can learn from them. It's hard. It's better than nothing because a lot of simple errors get easily caught. But yes, there is a problem of calling something from a very outside context, somewhere deeply nested in the tree. Any more questions about builders? Okay, so actually, it wasn't like there wasn't a single point when we finished designing extensions before the release of Kotlin 1.0. It was like an iterative process. We knew we wanted extensions from day one. So the very first conversation about Kotlin had extensions already on the whiteboard. And somewhere very early on, there was an explicit request. Let's try to support those. And we figured out how to put extensions and lambdas together to make it work. So it was kind of both were on the table.
Probably the most successful DSL is Gradle DSL.
Oh, yeah.
Collaboration early on, or?
It wasn't very early on, but well, it was fairly early after 1.0, but I don't remember when exactly. But yeah, so actually, the Gradle DSL is probably one of the most complicated in terms of implementation because it's two-stage. It has the configuration phase and the rest of the phase, and it's all very, very difficult. So it's a miracle that it works. Well, it's kind of, I think it's wrong to call it a miracle because I know people who made it work. It's a lot of work behind the thing that it works. And I think it's probably a decent trade-off that we made. Like we decided to put a lot of effort behind this idea, and it does pay off. But generally, trying to simulate the whole dynamic craziness of Groovy in a static language is a nightmare. So in this sense, I'm much happier with how Jetpack Compose worked out because there was no magic we had to reproduce from anywhere. There's a lot of magic, and there is a lot of compiler work behind this. But all this work was done outside the Kotlin team. So basically, all the design was done by the Compose team, and it was pretty cleanly integrated with the rest of Kotlin. So that is a similarly involved but much more elegant case of a DSL in Kotlin. More questions? All right. So what language is this? It does look like BASIC. Good guess. Yeah, it's actually Scala. And one thing that I don't completely understand is why folks over the Scala team are so proud of this that they put this into their manual. So yeah, so we had an explicit design decision of not supporting anything like that. So actually, you can do some of this in Kotlin, in fact, but no, we don't have like custom operators like this or those literals or many other things that Scala can do. So yeah, it was like explicitly decided that no, we're not trying to do anything like this. So what we had is kind of similar to C#, and actually we inherited a very interesting philosophy from C# that is kind of not very well advertised. So basically, in Kotlin, syntactic conventions never depend on interfaces. They only depend on presence of specific signatures, and this comes from C#. They have it the same with with their iterators and with link and many other things. So basically, we have a set of predefined operators. So you can't define your own, but you can overload these. You can do it with extensions. So you don't have to implement an interface to support this, which make DSLs easily extendable. You can add a DSL where no DSL was initially planned. And all interfaces still work, but they are like a special case of, special case of just having the signature at all. And thanks for C# for this idea. It was very useful. And also, soft keywords also come from C# and Delphi mostly. So thanks to the C# team and Anders Heilsberg for both those languages we learned from. Okay, the easy part is over. Let's talk about generics. Observation. Programming languages are weird. So here is Java at the top that creates arrays of foo with foo on the right, but then creates empty lists, a list of foo on the right, and empty lists with foo on the left. Why would they do that, right? And I know these people, they're very good. They know what they're doing. And then Scala comes along and it looks much nicer. Foo is on the right with list and empty list, but then arrays are indexed with round parentheses. Why would they do that? And I'm pretty sure those people are very clever too. Like, how come? Interesting, right? And the thing is, it's one can prove mathematically that this problem cannot be resolved, but it actually can be resolved in practice. That's the difference between theory and practice. So what do you think? How many named functions are called here? 2. What are the names? 2, foo and bar. That's one option. Any other options? 3 names. X, foo, bar, and x. You think x is a function? I don't think it's possible. It can be a function call there. Yeah, you can say plus is a function. Okay, I'll help you a little bit. So this is the same, right? And here's my help. How many functions are called here? 1, right? So 1 foo. Here, it's either a foo of function bar of 2 type arguments a and b, and a value argument x plus 1, or it's foo of bar less than a, b greater than x plus 1, right? And for the record, the case of the letters doesn't matter. The parser just sees letters. So for the parser, these two are the same. Parsers don't know the difference. And this is called an ambiguity in a language grammar. So in the grammar for Kotlin or C#, there is an ambiguity. And theoretically, this is an irresolvable problem. Like, you don't know how to interpret this, so you're stuck. You have to alter your grammar and either put your angle brackets on the left of the name. It would a salvaged bar right there at the top will know that this is not a comparison, but something else, because there will be a dot in front of this of the less than, right? Or you just drop the angle brackets because there are no angle brackets. There is only less and greater, and you use some other brackets like square brackets. So these are the paths that Java and Scala took. And Kotlin, after C#, said, okay, theory is nice, but we are engineers. We can hack things. So yeah, in Kotlin and C#, you create array lists with foo on the right. You create empty lists with foo on the right. You index arrays with square brackets. And if a parser encounters this, it tries to interpret it as a, prefers the type argument case. And if you really want it to be a comparison, put parentheses around it. It'll be fine. So yeah, so this is where practice beats theory. It's sometimes. Yeah, so we didn't invent it. We just stumbled upon the grammar problem and talked over to a C# team at JetBrains, and they told us, OK, this is not a problem, actually. We know how to fix it. So thanks, C# for this. Questions? OK. Another thing.
Do you ever consider making capitalization?
We did. So yeah, the question is whether we considered making capitalization important. We did. Unfortunately, with compatibility with Java, not all the APIs play nice by the rules. And like there's lots of classes named with a small letter and lots of functions named with a big letter. It just doesn't work. You can only impose such rules if you own the ecosystem from the start. It's the only, or if you have like a single mono repo where you can rename everything. Like when you have an open well, it does work. But thanks for the question. OK. Here is a generic higher order function, map, extends a list, takes a mapping function, returns a new list. Simple question, where is the type parameter A declared? Which occurrence of A is the declaration for the name? After the map, say this one. OK, this is actually the correct answer. So the problem here is that you can use a name, A, before it's declared. And this was supported in early versions of Kotlin, because when you do type checking, you don't go left to right. You don't care, actually, because you already have an AST and all that. But it's weird. And also, there are some stupid cases when it gets even weirder. So, and actually, you can see that here, it's an early syntax. We don't have it in Kotlin like this today. You can say f:'fun. Now, you say parameters, arrow, return types. And why? Because try to squint right just enough to figure out whether I close all the parentheses here. Because like all columns and parentheses, it's very, very confusing. So we went with a different syntax just because that one, it was like very elegant in terms of it was the same as the call site. Very nice, right? But it's impossible to read. So we killed this similarity to the declaration functions. We killed this similarity to the call site and put declarations in front of everything and put arrows to separate function types from just functions. Worked very well in comparison. Like there was this huge rename in the entire Kotlin code base at some point. It all got so much nicer.
These two are two independent problems, right? Like the declaration coming from just because you have the order.
No, these are not related. You can have one without the other, but it was kind of, we're trying to be as similar to the call site as possible, and like be homogeneous in terms of where generics go. So let's put the declarations after the name. Problem is we have extensions, so we had to give up that symmetry between the call site and the declaration site just to make it readable.
Why is this ordering?
Just for the human, it's pretty hard to spot these, to understand that these are declarations. So people were trying to put constraints, for example, here, because this is the first occurrence and they thought this was the declaration. It's like, it's super confusing for the user. You have a function, you want to add a new constraint, just a super type constraint, and just go for the first A and add there, and it doesn't work. It doesn't parse.
Probably broken that last colon with an arrow.
We did, and it gets worse. Yeah. So it's a very fair question. Yeah. So the thing is, so basically, this is the most common case. So we optimize for this case, and this case is the nicest when arrow is only here and colon is only here. If you can swap the two, but you can't. If you use an arrow here, you get confused already. Yeah.
So, it's the reason why you're order function and all these things. So, I find sometimes in Kotlin that the compiler understands functions to an extent, but there is not built-in support for things like currying or partial function application.
Mm-hmm.
Was this like a design choice or compromise?
That's a very good question. So I'll just repeat for the live stream. The question is, why doesn't Kotlin support currying or partial applications of functions or other functional language niceties that we have in other languages? And the answer is very technical. So basically, you can't implement it efficiently on the JVM, or well, yeah, on the JVM, it's absolutely impossible to implement efficiently. Other platforms differ, but basically, that's it. So I would love to have it. It's just not feasible. More questions? Okay. So a bit of history background on generics and generic-like features in different languages. So the concept of generics as such actually comes from functional languages. And there are type parameters on functions, and it's very natural. It's very uniform with value parameters, and very mathematically beautiful. Then the engineers' first attempt on a similar concept was C++ templates. And it's very powerful, very horrible. Nobody wants that again. And my understanding is that C++ community is kind of trying to tame their templates a little bit to make them a little less horrible. Then Java 1.0 and C# 1.0 had no generics whatsoever. There was a single generic type family arrays, and they were reified to an extent, and that was it. If you had a list, your get returns an object, cast away. So people kind of realized in a few years that it was not great, and there were interesting attempts in the Java community led by Martin Ojersky with the pizza language and then Scala, with the concept of erased generics, when we can basically, it's magic. So erased generics are a wonderful idea. Engineeringly, very beautiful. You can add generics to an existing library without breaking its clients. It's, wow, it just works because they are erased and all the binary signatures link at runtime as if there were no generics. Pretty cool, made the transition from Java 4 to Java 5 very nice and easy. C# went a different path. They just said, okay, there are a few classes in the standard library that requires rewriting for generics. We'll do that. They keep both class hierarchies for collections before generics and after generics to this day. If you implement a collection in C#, you implement two interfaces, one generic and one not. Tough luck, but that's tough luck only for collection implementers, basically. So, and they have reification, which means that generics are accessible at runtime. It's interesting. It has huge difficult implications on garbage collection, but nobody knew that in the year, I don't remember what, 1998 or something. In any case, we in the Java world are stuck with erased generics anyway. There are attempts at reifying them. It's expensive, it's difficult, so on and so forth. So we are using erased generics just because we have to support Java. Kotlin has erased generics, but we didn't take what we could drop from Java, and it was raw types. Raw types is basically a transition feature from Java 4 to Java 5 to make generic transition even nicer, to make not only runtime code not break, but also source code not break. Kotlin doesn't have raw types. Kotlin has black magic to understand Java's raw types. And like, it's mathematically a nightmare. Again, I mentioned that we used work of Ross State on types, and Ceylon also used his ideas, but they're differently. Basically, what we did, we talked to Ross, we took his ideas, we adapted them for practice, and there is little resemblance between his ideas and our implementation. But the names are there. So basically, yeah, Kotlin doesn't have raw types. Kotlin doesn't have stupid empty angle brackets because we didn't have compatibility requirements like Java 7 had. So that's nicer. But also, Kotlin doesn't have this. If you know Java, you probably had to learn that if you want to copy from something, you have to say question mark extends whatever super type, And if you're copying into something, you have to say !super that same type. And very many people are very confused. The sad thing is that the Java design team thought that this was easier to understand than an alternative proposal by Martin Odersky. And it's like super sad because everybody's confused by this and nobody's confused by Scala in this sense. In many other senses, yes, but not this. So this is basically a very unfortunate design choice. Unfortunately, it can be rolled back. So, but we have to support it because we have Java interpretability. So Kotlin has ins and outs. It helps a little bit. So at least there's no extends and super. You have out and in. If you are taking things out, you say out. If you're putting things in, you say in. It's not a huge fix, but it's a little easier. This is not the biggest thing we changed about generics compared to Java. And this is influenced by C#. C# has out and in as keywords in a similar sense in different place. They don't have it on the call side, only on the declaration side. The declaration side story is basically that alternative proposal that Martin had. The way Scala has it is plus t if you only take t's out of the list, and minus t if you only put t's into the list. It's actually wrong. It shouldn't say mutable list. It's right on the list, but whatever. So basically, the idea is very nice. If you know that your type behaves very uniformly across t, it only returns t's, directly or indirectly, doesn't matter. You can say out, and then everything is very intuitive. It's just like arrays. And a list of object is a supertype of list of string. Very nice, very simple. If you're doing it the other way around, if you're only taking t's, like you're a consumer of t, then it gets weird. It's called contravariance. You say the word in and get confused the rest of your life because contravariance is counterintuitive. But still, it's supported there. And you can build this. The good thing is that supposedly the person who writes the list class is the geek. And like his users may be ignorant of all this, and the word contravariance is not in their vocabulary. But they don't care because the compiler will tell them what's wrong, or at least that something is wrong. And they don't need to do this on every call side like here. So that's an improvement. So yeah, basically, Scala has traits and pluses and minuses. We do the same exact thing with the word interface and outs and ins. So basically, ideas from C# and Scala came together and made Kotlin interfaces. So, and Kotlin has mixed side variants where you can have use side ins and outs here and declaration side like on the previous slide. And the mathematics around this are a little crazy, but they work well. So yeah, so the good thing is you don't have to say extends for a list because we know a list is read-only, and you only say in instead of !super. Questions? Go ahead.
So one of the things that is interesting about Scala list to me is you can combine variants and things like higher kind of types. And this gives you type classes, and you can solve problems. Like I never understood why I couldn't just add two numerics in Java, and by in Scala you can do it thanks to type classes, right?
Yeah.
I see our folks and like some people in Kotlin trying to replicate it, but I've not seen this kind of support for this kind of by design. The look on your face.
Okay, it's complicated. So the question is basically, Scala has those two very nice things, higher kinds and type classes. Why doesn't Kotlin have them? So the answer is, so we didn't have it in the initial version just for simplicity. We wanted to ship. And higher kinds are, I think, they are very close to the border between reasonable and unreasonable. And I'm not sure on which side it is. So I was hesitant to add them in the beginning, and there are actually pretty few use cases for the wide range of applications. They're fairly specialized, actually. Type classes have many more applications than higher kinds. And there are different proposals on how to add type classes to Kotlin. And I think the Kotlin team is still considering them. It's not straightforward because there are different implications. There are type checking implications. There are runtime implications. But basically, it's doable. You have to be careful not to mess everything up too badly. And it's actually fairly closely connected to those receivers. Like you can relate the idea of receivers with type classes. And it's an interesting question, like how you design both for them to play nicely together. But yeah, basically type classes, I think, will make their way into Kotlin at some point. Okay.
So a question on genetics. One is
okay.
the other one is, as far as I remember, was it like because if you have more than one, it kind of hard to figure out which one?
Okay, so I'll start with the latter one. So Ceylon had a very nice idea of actually separating inferable and non-inferable generic parameters. It's very clever. It's very useful for the Ceylon use case because they base their optimization on it. It's nice for Kotlin. I mean, it's not we anymore, but I think Kotlin might adopt something similar at some point. I think that there is at least one proposal around this. Yeah, you'll have to. Yeah, I'll have to do something about it. And the second question is about reification. Like Ceylon had a very nice approach to reification of generics. The issue with reification in general is that it changes signatures for Java. So basically, every time you reify any generic parameter, you have to introduce a value parameter for Java to pass this type around, and it messes up APIs very badly. So basically, the explicit design choice was not to do it unless we absolutely have to, and we don't absolutely have to. That's it. All right. So I'm at the end of my slides. I'm happy you are still awake. Many things I didn't tell you about. Platform types. Actually, 2 or 3 years of my life went into platform types. Platform types make the thing work between Java and Kotlin in general. It's very interesting. It's not super complicated in the end, but the way there was pretty complicated. Coroutines, a great thing, not my area. I didn't even design them, so can't really speak about them. Delegate properties, very interesting, funny thing that's kind of sits on the side, but is very powerful and doesn't interfere with anything else very nicely. I like it very much for it. Unlike its counterpart, the delegation inside of inheritance, which is horrible because it interacts with everything and I hate it. Inline functions, great idea. Turned out like super useful. Many things work much nicer because of inline functions. Basically, we gradually turned them into something akin to macros, but with no harm of macros at all, which is wonderful. Macros are terrible for tooling, and inline functions are nice. Yeah, so some other time, probably. Yeah, key takeaways from this talk. Again, engineering is not about originality. It's about taking those great ideas and like working super hard to make them work together. That's the thing. Please use my ideas, like anything in your languages, in your talks, anywhere. And if you are nice and give credits, just kudos to you. Thank you so much. Yeah, I can take more questions, but feel free to just go to bed if you like. Go ahead. Yeah, thank you. So the question is, originality was not the goal for Kotlin, but looks like lambdas with the receivers are an original idea. Yeah, I would say yes. It wasn't seen in any other language before. So the static part of it. So people had lambdas with context before, but they didn't type them the way we did. So this is an original thing, but we didn't ask for it. It's just we had to add this bit to make the whole thing work. So I would say we did invent a few things along the way. It was never a goal. So we were very explicit up front about not being an academic language, not trying to invent new things, but we ended up inventing a few because we had to, basically. And platform types is another example of that. More questions? Mm-hmm.
Plans for making more type level algebra and stuff like TypeScript, for example, requiring the parameters to implement both.
Well, so you're connecting erasure to some type level algebra, is that right? Yeah. So my understanding is these two are not very closely connected because you can do type level algebra if you like, with or without erasure. It so happens that TypeScript has erasure as well, so we can do theoretically we could do every crazy thing that TypeScript does, and it does a lot of crazy things. But basically, there are a few things that are in high demand, like union types, for example, an ability to say this is A or B. It's possible to introduce it into Kotlin. It will complicate type inference quite a bit, but otherwise it will not break anything else. So my understanding is it's still on the table. It's just a lot of work for the compiler team to make it like play nicely with all the type inference stuff.
I have a question around Kotlin multi-platform. The original legacy compiler was mapping data classes to regular JavaScript objects, and then that kind of got taken away in the newer version of the compiler. It kind of broke interoperability a little bit, or took it away. I was wondering if there's any reason for that.
I'm sure there are. I do not remember, unfortunately. So the story behind the JavaScript interop is basically we're trying to fit into the untyped, unstructured JavaScript world as good as we can, without losing Kotlin's guarantees too much. We lose some, but not all of them. So I think what you're talking about is some sort of a trade-off. I don't remember exactly because I was not on the design committee for that one. But it's probably motivated with some very long chain of examples and difficulties, and it's a trade-off. That's all I can say.
What would you take out?
Oh, what would I take out of Kotlin? Let me see. So one thing, yeah, absolutely sure. I would remove inheritance by delegation, because it's a nightmare in every possible way. It looks like such a nice feature when you first think about it, but then you try to make it play nice with everything else, and man, it's not extendable in any way. Like, there is a request, very long standing request, like we want access to the delegated object, to the delegate, because it's absolutely intuitive. You need this object. You can't make the language work around this. Like, when you try to introduce, you either have to introduce lots of new syntax, like specifically for this use case, and it's like a big part of syntax, or you get all sorts of nasty interactions and things break down. So it's actually a carryover from a bad design idea from the very beginning. We wanted fully fledged multiple inheritance in Kotlin in the very, very beginning. And the only way to do it on the Java platform, it doesn't work anyway, but the only idea was to use delegation to just delegate to different superclasses and so on and so forth. It couldn't work. We didn't understand it from very early days. We understood it fairly quickly, but some delegation code was already there, and the by thing looked so nice, and we just kept it, and people used it and loved it, but you can't do anything with it. Yeah. Say it again.
That's now within inline classes because you make things
Yeah, so I think inheritance by delegation is the most resisting feature to any design changes. Like it's trying to stay the way it is and just fights any sort of extension. It's like super hard. Another thing I don't like is companion objects. We took the idea from Scala. It looked nice on the surface. Like you get rid of all the statics and so on and so forth. The sad fact of life is that statics are there. They're real. They're needed. And this way of kind of sweeping them under the carpet didn't work all that well and introduced bulky syntax that nobody's happy with. So yeah, I would definitely take them out. Yeah.
I'm curious, was Kotlin your first experience as a language designer? I guess it's very different from...
As production language designer, yes. As I was doing research on domain-specific languages before Kotlin. And actually, it's just a coincidence, but my first job as a programmer was implementing an ID for an interpreted language. If some of you remember, there was a thing called UML. And around UML, there were more weird things like QVT, the Query View Transformation Language. And I was working on implementation of that language and debugger for it and so on and so forth. And it was messy in every possible way. But I think I got my first practical experience working in languages then. I was a junior developer, like it wasn't designing anything. It wasn't even that team that designed the language. But yeah, basically, I didn't design anything that anybody else used in any reasonable extent before Kotlin, but I spent a lot of time working on different approaches to doing languages, different meta languages, so on and so forth. So I had a lot of background, but no production experience.
So one of the things about JetBrains is that you designed the language, but also designed the tooling, and tooling was there before Java and other languages. During the Kotlin development, does both teams talk to each other about the tooling, or how does the delivery of the language into tooling look like?
Yeah, it's a great question. So the question is like, how did the tooling team and the language team communicate inside JetBrains when we're working on Kotlin? The answer is interesting. What is the same team? It was for a long time there was no separation between the tooling team and the language team. So we had an IDE before we had a compiler. It's in retrospect, I think it may not be such a great idea as we thought then, but just because basically we made an IDE-centered compiler, which is not a great compiler, and is not great for an IDE either, basically, because it's like a nasty compromise between the two, and we should have done it differently. But the structure of the team was that everybody worked on everything. There were dedicated people working only on the back end at some point. But generally, I worked on the IDE and the compiler and everything. And so basically, I think the compilers, the Java interop part of the compiler still uses a huge chunk of the IDE today. Because to analyze Java code, to import Java declarations, we use a part factored out of the IntelliJ IDE, which isn't, again, great for a compiler, which should have used Java C or something, but it was the easiest way to do it. Yeah, thank you.